So when the news of DeepSeek came out, it caused a stock market crash that lost over $1 trillion in one afternoon. And now we have this. Berkeley researchers replicate DeepSeek's R1 core technology for just $30. Will this cause a global financial meltdown, the likes of which we've never seen before? Probably not, but it's still very, very cool. As they say here, it's a small model reinforcement learning revolution. So a Berkeley AI research team led by PhD candidate Jai Pan has achieved what many thought impossible, reproducing DeepSeek R1's 0 key technologies for less than the cost of a dinner for two. So here's their post on Twitter. I'll link it down below. It's got a GitHub. It's got all the experiments, all that stuff, so people can copy it, download it, reproduce all the findings, and test it out for themselves. As you can see, he's saying you can experience the aha moment for yourself for less than $30. The aha moment is, if you recall from the R10, that paper that we covered a few videos back, it's kind of interesting. It's kind of mind-blowing. And that is that we can use reinforcement learning to have these models kind of almost learn on their own. As the people in the research paper put it, it's self-evolution. Eventually, this model discovers it has these emergent abilities that are fairly advanced reasoning abilities and strategies that aren't explicitly taught to it. Now, of course, that's a large model that, they were put together by a large lab, still millions and millions of dollars. But what does this mean? Does this mean that we can reproduce that incredible, self-improving learning ability for less than $30? This might be a lot bigger than it appears on the surface. It's a little too early to tell, but let's dive into it. This has my spidey sense tingling a little bit. All right, so they continue. So this is from XYZ Labs. It's a Substack, basically a kind of a write-up of what was posted on Twitter, on X. They're catching some flack for not posting posting the original author's GitHub and X.com post. So I'll make sure I'll link all of this. So just to be clear, so this is the person that did all the work. This person sort of just did the sort of a summary, a write-up of it. And now here I am doing a sort of a dramatic reading of it, if you will. Don't think about it too hard. We're all going to get replaced by robots very, very soon. Let's continue. So their success in implementing sophisticated reasoning capabilities in small language models marks a significant democratization of AI research. And depending on what the implications here are, again, it could be potentially a lot bigger than that. But so here are the key achievements. So first and foremost, successful replication. Again, we're talking about the R10s, sort of they've replicated some of its abilities. We'll talk about specifically what. They didn't replicate the entire model, but as you'll see in a second, that might not be needed. So they've replicated that under $30. And so here we're talking probably the cost of compute. Keep in mind that's rapidly falling. So in a year, 2 years, 3 years, that's going to be a lot less for sort of the same amount of compute, and even more if you're taking the various sort of algorithmic improvements into account. Yesterday, we covered Dario Amadei's post, and one of the interesting things in it, he said how quickly the cost to run this stuff, how quickly it's falling. And that cost is falling due to not only just, the hardware getting better, but also the algorithmic improvements. So we're getting more efficient at using that compute to do more. So when we're just talking about the algorithmic improvements, so assume no improvements in NVIDIA chips or anything else like that, just sort of like the software and how we tend, the architecture, how we tend to run it. So back in 2020, he published a paper with his team suggesting that it's about 1.68 times a year. He's saying the number today is maybe 4x a year. So just keep that in mind because, $30 isn't a lot of money, but keep in mind that this is going to be less and less money for that same thing as the years move forward. Eventually, this will be negligible, it'll be pennies. And so they're able to create complex reasoning in small models. So 1.5 billion parameters is tiny. Usually when we're talking about small models, we're talking about something like 7 billion. Medium models are 70 billion. And then on the large side, we have something like 450 billion or 405 billion. Meta's Llama. We believe GPT-4 was something like 1.7 trillion. So this is 1.5 billion. It's sort of even less than usually what we refer to as small. This is like a tiny model that develops complex reasoning. And the performance is comparable to larger systems. Again, so they're trying to replicate the R10. So they've used the countdown game as their testing ground. So as an example, so here they're saying use the numbers 19, 36, 55, and 7 to create an equation that equals 65. So you're supposed to take those four numbers and use basic arithmetic operations to make that equal 65. So as you can see here, we have sort of the chain of thought, right? So the thinking part of it, and here we have the answer. And so one thing to keep in mind, so as the author of the paper puts it, one caveat, of course, is that it's validated only in the countdown task, but not the general reasoning domain. We are now bounded by compute, and please reach out if you want to help. Somebody please give this man whatever he needs. Because again, I think really what this comes down to is like how general will these findings be to what different problems can we sort of apply this? We'll unpack that in just a second. But the point is, so this implementation showed models evolving from random guessing to sophisticated search and self-verification techniques. One other sort of cognitive task that they gave it was, for example, for number multiplication, the model instead learns to break down the problem using a distribution rule and solid step-by-step. So again, kind of the big thing about the R10 was the fact that we weren't teaching it explicitly how to do problem solving. We created the right sort of reinforcement learning environment, and it figured it out. So mind blown just a little bit, right? So the paper isn't published yet, paper coming soon, but what this seems to indicate is that same sort of self-evolution, that sort of aha moment can happen not just in these large expensive models, but also in these, $30 models. And those models will cost $8 next year and then $2 the year after. So actually cheaper than that if you assume NVIDIA is going to keep cranking out better and better chips. What's kind of fascinating here is, so they worked their way up from the smallest 0.5 billion model, right? So 500 million, and they worked their way up. And so those models, they can only manage basic guessing, so kind of useless. And at 1.5 billion and upwards, they demonstrated remarkable problem-solving capabilities. So as we move up the models, like at 1.5 billion, we start sort of seeing these emergent abilities. So this is sort of a much lower. It's much smaller size of the model that we're beginning to see this than I think most people would have guessed. They mentioned that sort of the reinforcement learning algorithm, so kind of like what approach that they're using, it's less critical than expected. And so here's where we're kind of getting to the crux of the issue here, right? So one of the most fascinating discoveries was how models developed distinct problem-solving strategies for different tasks. In the countdown game, they mastered search and self-verification. For multiplication problems, they learned to apply the distributive law. This suggests AI systems develop specialized rather than general problem-solving approaches. So for those that may have missed the DeepSeek R1, so this is the paper out of DeepSeek, right? So they've introduced the R1, so that's the big thing that we've all been hearing about recently. That and the V3, that's the other model. But here in the paper, they also talk about the R10. So just a quick 20-second summary is what they did is they used reinforcement learning to kind of have this thing try to learn and improve itself through kind of self-evolution. In the previous video, we've broken down exactly kind of like what that means. We're not going to go through that again, but the point is it relied less on humans and humans guiding it and more on just like, hey, you figure it out. You, the model, you figure out how to solve these problems. And what they've noticed is it demonstrates remarkable reasoning capabilities. It naturally emerges with numerous powerful, intriguing reasoning behaviors, right? So the R10, the self-evolution process of it, right? So it's improving itself. It's learning how to solve problems on its own, right? They're saying that this is fascinating that the reinforcement learning can drive a model to improve its reasoning capabilities autonomously, right? So this model naturally acquires the ability to solve increasingly complex reasoning tasks by leveraging extended test time computation. So basically here it realizes that, it can think for longer. It can do longer outputs to figure out kind of like what's true, what's not. It can do longer responses, and that gives it sort of better accuracy, better problem-solving capabilities. And they notice the emergence of sophisticated behaviors such as reflection, right? Where it revisits and reevaluates its previous steps to find, alternative approaches. These spontaneous developments significantly improves its own reasoning capabilities. And so this is what they're referring to as the aha moment. Now, interestingly, there's certain phrases in these papers that become, catchphrases. They're memes. They become mimetic, right? The attention is all you need paper kind of said its own thing, where now a lot of people are like, well, this is all you need, or that is all you need. It kind of became like a thing. The aha moment, I think, as far as I know, this is like the first time I'm hearing that idea. And I think it was this paper that started. I think it's going to start like a thing where people will be referring to something specific as the aha moment. And the aha moment is basically where the model on its own figures something out. So in this case, it just figures out that it needs to allocate more thinking time to a problem through some self-reflection. I don't think it necessarily matters what it figured out, but the point is it figured out on its own without us explicitly trying to tell it how to do it. And this is showing how reinforcement learning can lead to unexpected and sophisticated outcomes. This shows that these models are able to autonomously develop advanced problem-solving strategies. If you're a longtime watcher of this channel, thank you. You've heard me talk about this situational awareness by Leopold Aschenbrenner. Right there, he predicts quite a few things, some of which we're literally seeing coming true right now, specifically kind of like the interplay between the state, right, the United States, for example, and all these AI labs. I think he kind of nailed a lot of those predictions. This other prediction was about the intelligence explosion. And so he's kind of projecting that somewhere in, call it 2026, 2027, which is, by the way, similar to where Dario Amodei is putting it. Dario saying that that's kind of the point where we're going to expect to see these models become better than humans at most tasks. And of course, sort of like one of the tasks that the humans do is AI research. Right. So what happens when AI is better at improving AI than humans are? And at the time, so there's a lot of people, when this came out, there's a lot of people that kind of like came out kind of criticizing it and saying why this is silly, it's science fiction, it's not going to happen. You know, Sabine Hassenfelder, love her, really respect a lot of things that she does. So she put out a video about that exact thing. You can see the screenshot from the paper in the background. So here's kind of her conclusion. And she did a great job of sort of summarizing kind of what everybody was thinking about this at the time, why this wasn't a realistic scenario.
Where I get off the bus is when he concludes that this will lead to the intelligence explosion, accompanied by extremely rapid progress in science and technology and society overall. Do you get off the bus and miss the boat, or get off the boat and miss the bus? These damn English idioms always throw me off.
So a couple points about that. Number one, it's interesting to hear that Sabine has trouble with English idioms. It's very endearing to know that she wakes up one shoe at a time, just like the rest of us.
The reason I don't believe in Aschenbrenner's predictions is that he totally underestimates the two major limiting factors, energy and data. Training bigger models takes up an enormous amount of energy. Honestly, I think these guys have totally lost the plot. They're living in some techno-utopian bubble that has groupthink written on it in capital letters. Then there's the data. Okay, so you've trained your AI on all the data that was available online. Now what? Where are you going to get more data?
So the two kind of big bottlenecks that a lot of people were mentioning is number one, energy, number two, data. Now with data, of course, we're seeing a lot of synthetic data produced. So the reasoning of the models, as it kind of outputs its rationale, it's thinking that can be used to improve the next generation of models. That's what we believe OpenAI is doing. They had their O1 that led to the O3. O2 was somebody else's trademark. And according to one of the senior leadership that recently did an interview, they're saying they're building the next sort of stage, the next model already. They're training the V4 or whatever they're going to call it. O4, whatever. And of course, energy is sort of the other thing that's limiting this thing. But this was before DeepSeek and their close to 50% sort of a reduction in how much compute it costs to create these models. So whose world will we live in? Is it Aschenbrenner's or is it Hassenfelder's? I have no idea. I'll leave it up to them to figure it out. But this idea of automated AI research, it just doesn't strike me as insane because keep in mind, DeepSeek is a Chinese company, right? So very different culture. They're not part of that Silicon Valley. They're not trying to, raise funds raise money from venture capitalists. Very different social dynamics, very different sort of like government state dynamics. But it seems like they're also seeing something emerging here. And that's kind of similar to the thinking here on the sort of US side. So they're saying reinforcement learning, right? And this idea of the aha moment of self-evolution, right? It has the potential to unlock a new level of intelligence in artificial systems, paving the way for more autonomous and adaptive models in the future. This is what Ilya Sutskever said a number of years ago, saying like these transformers, these neural nets, they just want to learn. Does it feel that AI progress right now is this uphill battle where we have diminishing returns, which, every step forward we take gets harder and harder? I really don't think so. I think it's exactly the opposite. There's this snowball effect where each development, whether that's from the US side or anyone else in the world, certainly the things that this Chinese company introduced, massive breakthroughs. So people are saying, oh, well, they copied the US firms. They did the distillation from the US firms. And if I had to bet, I would bet that they did, in fact, do that. But I am also 100% sure that every American company did that to each other, or probably starting with the GPT-4. A lot of this AI wave was largely triggered by Google when they put out their attention is all you need paper, right? The transformer architecture. So it's I mean, that's how science should be, right? We're all putting stuff out there. Everybody's copying it, building on top of it. These new breakthroughs that DeepSeek proposed, like the more efficient ways of making these neural nets. I mean, you know that OpenAI and Meta and everybody else will be using those very, very soon. That's how progress works. That's how science works. But what I think this paper, it's not a paper yet, but what this research is showing, and again, we're going to see how big of an impact this will have, it might be massive, is that number one, that's sort of like self-evolution, that sort of aha moment. And notice he says here, you can experience the aha moment for yourself for less than $30. He's referencing the R1 paper. I guarantee you it's a thing now. But the surprising finding here is that how small the model is, like that sort of like the threshold for the size of the brain of the neural net is much smaller than we expected to start developing these sophisticated, quote unquote, sophisticated reasoning abilities. The fact that that's self-evolution, that's sort of its ability to figure out, how to solve problems on its own without us explicitly telling it. So that implicit learning, implicit understanding, that starts off much sooner. It sort of emerges in models much smaller than I think most people would have anticipated. I think that's very fair to say. So really fast, it's important to understand that. So Google DeepMind had their sort of like the alpha systems, right? So they have a lot of notable projects prefixed with alpha, right? So you have AlphaGo, destroys professional human Go players. They have AlphaGo Zero, sound familiar? An evolution of AlphaGo. AlphaGo Zero, learn to play Go without any human data, solely through self-play, achieving superhuman performance, right? Then we have Alpha Zero, so the same principles, but for anything, chess, shogi, Go, whatever. AlphaGo figures out these highly complex 3D protein structures, like you get the amino acids, and it's like it figures out the 3D structure. The chain of amino acid, it folds into a protein within super fast, like seconds. And once it folds, it has certain abilities, the abilities of the proteins that make life possible. The number of different variations into which it can fold, it's something like, it's more than the number of atoms in the known universe. It's not just like astronomical numbers. It's like beyond that. It's some like insane number of possible configurations. AlphaFold predicts those, right? We have AlphaCode for coding. We have AlphaTensor, AlphaGeometry, AlphaProof. So these two together almost got the gold medal at the IMO, the International Mathematical Olympiad. So they're saying a performance comparable to that of a gold medalist. So yeah, I think it was 1 point away from getting the gold medal. So why are they all called alpha? So they're using a lot of the same sort of a recipe for building these models, and a lot of it is sort of reinforcement learning. So reinforcement learning is when we reward behaviors we want, good behavior, and also you can have negative, sort of like punishing or penalizing the behavior we don't want. So the point is, a lot of this, they applied those ideas to specific things. Like, let's see if we can apply that idea to habit code. Let's see if we can apply this idea to have it figure out how to do, protein folding. That same idea for playing chess and StarCraft 2 and Go, etc. Now we're entering a period where we're kind of using those same ideas, how to have the AI improve itself through reinforcement learning. We're sort of taking that piece and we're adding it on top of our knowledge of these large language models. And this is where this magic seems to be happening. So we covered this yesterday, but really fast. So he's saying that the highest leverage thing you can do for open source, and if you're just trying to do more good stuff with machine learning, with AI, he's saying construct a high diversity of reinforcement learning environments that help elicit LLM cognitive strategies to build a gym of sorts, right? And this can have a massive impact for everybody that figures out the sort of reinforcement learning strategy for their own specific corner of the world, for their own task that you want these large language models to do. A lot of people doing this, all over the world and contributing to the open source community. This would be massive. So I didn't know this, but I actually just saw this. So Andre did retweet this exact thing that we're looking at, right? The $30 R1 replication. And he also just recently posted this, which is actually a great way to understand kind of like what we're talking about. So he's saying, like, let's say you open up a textbook to start reading about something new that you're trying to learn. There's three major types of sort of data of information within that book. One is like the background information, the exposition, sort of like the lessons, right? And that's similar to pre-training for these neural nets, for these AI models, right? So this is where the model is just like reading the internet and accumulating background knowledge. As you read a textbook, your brain is, pre-training for doing that thing. Next, you have worked problems with solutions. So this is supervised fine-tuning. This is where the model is fine-tuned on ideal responses for an assistant written by humans. So you might have in your textbook, like, here's a problem and here's how you would solve it, right? And by the way, R10, this is the part that it skipped and instead it tried to have the neural net, the R10 model, kind of learn everything by itself, right? So here's that paper, DeepSeek R1. It was trained without supervised fine-tuning. Right, so that's supervised fine-tuning, and we also have the practice problems. And these are prompts to the student, usually without the solution, but always with the final answer, right? There's usually many, many of those at the end of each chapter, so you can practice how to do stuff. And this is equivalent to reinforcement learning. So what does all this mean? Well, first and foremost, it really sounds like large language models and then sort of this reinforcement learning, RL training, like a gym for the model, as Andre put it. That approach seems to be incredibly, incredibly powerful. A lot of people that are talking about super intelligence, they're probably, one of the reasons they're saying it is because that's the approach that they think will lead to it. We have some incredible contributions to the open source ecosystem. Andre Karpathy is even suggesting how people can take it even one step further by building these sort of reinforcement learning gyms for the neural nets. And so again, those things are massive. They're happening right now. This is part of the reason why we're seeing such, big breakthroughs, etc. But then comes this paper, the, $30 replication of R1. And so it's important to understand that, number one, it doesn't replicate all of R1. It's sort of only certain specialized tasks. So it's more like AlphaGo 0, right? It just plays, the game of Go. It doesn't do everything. But at the game of Go, it's superhuman. So if this holds up, it sounds like we can train these small, tiny models to be, excellent, maybe superhuman at very specific tasks. And unlike training the large models, this can be done extremely cheaply. The models can be tiny to the point where, and I think, and this is just kind of me kind of extrapolating this might not come to pass. Again, it really depends on how applicable this sort of is. And I'm sure we're going to be seeing a lot more of this coming out. So over the next few months, we're going to see the nature of this, the reality of this emerge. But I mean, imagine being able to spin up a sort of like a superhuman AI model for one specific task that you're trying to do for just like a few bucks, for $20, for, specific projects that you might be trying to do, for specific business automations that you're trying to do. So what this means is if you have just like one specific use case, you can create incredibly cheap and very, very powerful models that are just for that use case. So for example, if you want like a medical triage, for example, where people need to know, like, if this is happening, do I need to go to the emergency room or what? An accurate, rapid, low-cost screening tool like that would be incredibly inexpensive and can free up, the hospital staff from having to do everything by themselves. Also, it would help trigger like the more like advanced stuff, the more dangerous cases, flag them for the doctors, etc. You can have an incredibly high precision legal document review, right, for specific use cases. Or let's say you're like a celebrity, a Hollywood actor, and you need some very specific things that you need to review. A very simple, cheap model can be created to do that thing, and probably that thing only, but extremely, extremely well. You can have a targeted sort of customer support chatbot, right? Targeted for just like one product or one services, but like with incredible knowledge in that specific thing. So imagine if you're like a supplement company, right? There's tons of stuff that has to be like very specific. Now, as we learn more and more about the DNA and the mutations and stuff like that, there might be certain supplements or certain conditions that might be just fine for one person, but cause issues in another. Having a chatbot that's, again, much better than any human at being able to give you like the best advice on which sort of supplement to take, etc. All of these would be lightning fast, very inexpensive. They could be continuously learning and improving. So again, big thanks to the people behind this. Very interesting. I can't wait to see how far this could be applied, right? So if we can build these tiny, cheap, and expensive models for like any cognitive task, well, a Cambrian explosion of reinforcement learning on LLMs begins. And the Cambrian explosion was, of course, the time of rapid, this explosion of evolution hundreds of millions of years ago. And certainly it seems fitting now with the open source community, with everybody contributing their own sort of reinforcement learning gyms, as Andre Karpathy suggests, and just the power of these neural nets. Yeah, we're at a threshold of something very, very special here. If you made it this far, thank you so much for watching. My name is Wes Roth, and I'll see you next time.